There is a math problem in Silicon Valley that nobody talks about. We have the chips to run artificial intelligence, we have the data centers to house them, but we have run out of the one thing that makes them work: electricity. The US power grid is full. You cannot build new transmission lines fast enough. You cannot build natural gas pipelines fast enough. And wind and solar are physically too spread out to power the gigawatt-scale clusters that AI requires. So big tech is rewriting the rules of physics. Instead of bringing the power to the data center, they're building the power plant inside the data center. And they're doing it with the most controversial technology on Earth. This is the story of the $80 billion bet on pocket nuclear. Here's the problem. AI is chewing through electricity faster than the grid can grow. Training a single frontier model, something like ChatGPT or Gemini, uses as much power as 120 American homes consume in an entire year. And once it's trained, the demand doesn't stop. ChatGPT alone burns through roughly 564 megawatt hours of electricity every single day just answering our questions. Zoom out, and it gets even more unsettling. Data centers already use around 4.4% of all US electricity. By 2028, that share could climb to roughly 12% as AI systems scale up. By 2030, those loads could easily double or even triple as more powerful models come online. Wall Street can see what's coming. Goldman Sachs estimates the US will need an extra 85 to 90 gigawatts of new generation by 2030 just to keep up with AI and data center demand. That's roughly the same as building around 90 large nuclear reactors in the space of 5 years. Which is why Silicon Valley is quietly looking at a very different kind of solution. But before we get there, it's worth asking a simple question. If AI needs this much power, why can't we just use the energy sources we already have? On paper, the first choice is renewables. Cover the desert in solar panels, line the plains with wind turbines, and plug AI straight into clean energy. In reality, there's a catch. None of it is there when you need it most. Solar panels shut off the second the sun goes down. Output crashes on cloudy days. Wind farms can sit almost idle for hours when the air is still. Batteries help, but only for a while. They can shift power across part of a day, not keep multi-gigawatt data centers running through long lulls. So you fall back on the thing that can run all night: fossil fuels. Natural gas plants are dispatchable, already built and hooked straight into the grid. From a grid operator's perspective, they're the easy button. But from big tech's perspective, they're a trap. Amazon, Google, Microsoft, all of them have publicly committed to running on carbon-free energy by 2030. Leaning harder on fossil fuels doesn't just blow those targets, it invites a backlash from regulators, investors, and their own users. So if you can't rely on gas, and you can't build enough wind and solar with batteries to cover a 24/7 AI load, what's left? Nuclear. But you still have a problem with that because AI wants power on software timelines. No one in Silicon Valley is going to sit around for 15 years waiting for a traditional nuclear plant to be poured and welded together in the middle of nowhere. That's why they're reaching for something that sounds almost impossible. Nuclear power you can build in a factory and ship on a truck. They're called small modular reactors, SMRs, and their even smaller cousins, microreactors. Let's break down what that actually means. Traditional nuclear is built around a familiar picture: a large core of uranium fuel rods sitting in a tank of water. The water has two jobs. It cools the fuel and it carries heat away to make steam and spin turbines. To do that safely at the scale we're talking about, often around 1,000 megawatts of electricity from a single reactor, you need enormous pumps, heavy piping, redundant backup systems, and a containment building that's essentially a concrete fortress wrapped around the whole thing. It works, but it's complex, bespoke, and incredibly hard to build quickly. Small modular reactors flip that model. Instead of a single gigawatt class unit, you shrink the reactor down. Most SMR designs sit below 300 megawatts of electric output, with some individual models in the 50 to 100 megawatt range. Some designs swap out water for helium gas or molten salt as the coolant. These fluids can run at much higher temperatures without boiling, which changes the way the entire system is arranged. You no longer need the same kind of high-pressure water loops or the giant emergency cooling systems that dominate a conventional plant. A lot of the advanced concepts also change the fuel itself. Instead of long metal rods, they use tiny ceramic-coated fuel particles packed into graphite. Each particle engineered to trap radioactive material inside even at extreme temperatures. The idea is that if something goes wrong, the fuel can simply ride out the heat and hold everything in place long enough for the system to cool down without needing the same scale of last-ditch intervention. Go smaller again, and you get to microreactors. Machines in the 1 to 5 megawatt range in current defense projects, with some concepts stretching towards 10 or 20 megawatts. They're designed to fit inside a handful of 20-foot containers, move by road or rail, and simply plug into a microgrid when they arrive. Once you can do that, you can move a lot of the hard work away from the site and into a controlled manufacturing environment. Components are built, tested, and repeated under the same conditions, instead of being reinvented from scratch in the mud and weather of every new project. On paper, that's the key difference. Traditional nuclear is a custom one-off. These new designs aim to be a standard kit that just happens to produce megawatts instead of smartphones. Whether that vision holds up in the real world comes down to one thing: the numbers. On one side of the ledger, you've got the old model. Projects like Vogtle in Georgia were supposed to be the template for the new wave of large nuclear plants. Instead, they turned into a warning. From first concrete to full operation, the two newest reactors took roughly 15 years and ended up costing around a whopping $35 billion. Impressive engineering, but a financial horror story. On the other side, you've got the pitch for SMRs and microreactors. A full-scale plant might still run into the low single-digit billions, but instead of 1 or 2 colossal units, you're talking about a cluster of smaller reactors, each designed to be built over and over again. Developers talk about 3 to 5 year timelines for first units, stretching to maybe 7 years for multi-module sites. Still a long time by tech standards, but much closer to the AI roadmaps that top out around 2030. Put simply, big nuclear is a $30 billion 15-year bet. Pocket nuclear wants to be a $1 to $3 billion 5 to 7 year product. The surprising part is who's testing that claim. Because over the past year, some of the world's biggest tech companies have quietly started turning that theory into contracts. In October 2024, Amazon did something no cloud company had ever done before. It led a $500 million funding round for a nuclear startup called X Energy and signed up for its first SMR project in Washington state. The plan starts with 4 XC100 reactors delivering 320 megawatts of power, with an option to scale up to 12 units and 960 megawatts on the same site. That's almost a gigawatt of carbon-free power tied in part to Amazon's own data center footprint in the Pacific Northwest. By the time the first modules are built out, total project costs are expected to be well into the billion-dollar range. 2 days later, Google made its own move. It signed a first-of-its-kind agreement with Kairos Power and the Tennessee Valley Authority to develop a new advanced reactor in the US. The first unit, called Hermes 2, is designed to deliver around 50 megawatts of nuclear power to the grid by 2030, with a roadmap that could grow that to 500 megawatts across multiple units by the mid-2030s. That electricity won't be directly wired into Google's buildings, but the whole point of the deal is simple. Add enough clean baseload to the same regional grid that feeds its AI data centers in Tennessee and Alabama to keep them running around the clock. Microsoft took a completely different route. Instead of backing a brand new reactor design, it signed a 20-year deal with Constellation Energy to restart one of America's most famous nuclear plants, 3 Mile Island Unit 1. The unit that melted down in 1979 will stay shut, but the undamaged reactor next door, now being rebranded as the Crane Clean Energy Center, is being brought back to life. When it returns to service as early as 2027, it will add roughly 835 megawatts of carbon-free power back to the grid. The restart itself is expected to cost around $1.6 billion, backed in part by a $1 billion federal loan. A huge chunk of the output is reserved for Microsoft's data centers under that long-term contract. Then there's Meta. In December 2024, the company quietly released a nuclear request for proposals, effectively a shopping list sent to reactor developers. The ask was big, between 1 and 4 gigawatts of new nuclear capacity in the United States, with first plants coming online in the early 2030s to support AI and social media workloads. Meta hasn't picked a specific design yet. The RFP is open to both advanced small reactors and more conventional plants, but the scale tells you everything you need to know. This isn't about one experimental unit. It's about building enough nuclear to rival a small national grid. Oracle, meanwhile, is thinking even bigger on a single site. Chairman Larry Ellison has talked publicly about designing a gigawatt-scale AI data center campus powered by 3 small modular reactors, with building permits already in place for those units at the chosen location. There's no detailed schedule or vendor list in the public domain yet, but the intent is clear. Instead of hunting for spare capacity on a crowded grid, Oracle wants to bolt its own private nuclear plant directly onto a cluster of cloud facilities. And those are just the headline names. Behind them, companies like Oklo are signing huge framework deals, up to 12 gigawatts of advanced reactors for data center operator Switch alone, while other hyperscale operators explore similar agreements and letters of intent of their own. Taken together, the pipeline of nuclear projects explicitly linked to AI and cloud infrastructure already runs into the tens of gigawatts, the rough equivalent of 20-plus large reactors if even a fraction of the announced capacity is built. Put a very simple price tag on that, say around $3 billion per gigawatt for advanced nuclear, and you're talking about tens of billions of dollars in potential investment. If the bigger options and follow-on phases go ahead, the total easily pushes to around the $80 billion mark over the next 2 decades. For the big cloud providers, that's the trade. Gamble on a new kind of reactor, or accept that the growth of AI hits a hard ceiling. And this isn't just about Silicon Valley's power bill. The same reactors that could sit behind a data center are already being written into national security plans and into a much bigger geopolitical race. In October 2025, the US Army launched something called the Janus program. Its brief is surprisingly simple: get a microreactor up and running on a military base by September 2028. The logic behind it is brutal. For years, Pentagon studies have warned that fuel convoys are some of the easiest targets in a conflict zone. Every liter of diesel you truck into a remote base comes with a human cost. A reactor you bring in once, inside something not much bigger than a shipping container, flips that equation. Instead of protecting long fuel lines, you defend a single hardened site that can run for years without refueling. And then there's China. While the US is still talking about first-of-a-kind projects, China already has an advanced small modular reactor in commercial operation at Shidao Bay, feeding power into the grid. It's a high-temperature gas-cooled design, the kind of technology Western companies are only now trying to commercialize. That matters because the AI race and the nuclear race are starting to overlap. Whoever can build out reliable, low-carbon power fastest gets a structural advantage. More chips, more training runs, more models. Energy infrastructure becomes part of the competition. For all the hype, not everyone thinks this is a good idea. In 2024, the Union of Concerned Scientists argued that small modular reactors aren't automatically safer than the big plants we already have. Nuclear expert Dr. Edwin Lyman has warned that some designs are being allowed to use smaller containment structures, reduced emergency planning zones, and fewer on-site security staff, essentially relaxing the rules because the reactors are smaller. The industry's response is that advanced fuels and passive safety systems make severe accidents far less likely in the first place. Critics counter that until we've seen these designs operate at scale, that's still a promise, not a proven fact. The clock on this is brutally short. By the late 2020s, Microsoft wants 3 Mile Island Unit 1 back online, feeding around 835 megawatts of nuclear power into its AI and cloud workloads. Around 2030, Google's first Kairos reactor in Tennessee is supposed to start up, while Amazon's Cascade project in Washington is planned to grow from 320 megawatts of XE100s toward nearly 960 megawatts through the 2030s. Meta is chasing another 1 to 4 gigawatts on top of that. Put all this together and you get roughly 26 gigawatts of nuclear capacity on the table. At today's prices, that's an $80 billion bet that factory-built reactors can show up on time, at cost, and at the scale AI is going to need. If it works, nuclear stops being a one-off megaproject and starts looking like a repeatable product, unlocking trillions in clean energy builds well beyond AI. If it fails, the fallback is simple and ugly: more gas plants. Do you think Big Tech's $80 billion nuclear bet is going to pay off, or is this heading for a very expensive dead end? Let me know in the comments, and if you want more deep dives like this, make sure you like, share and subscribe for more mega build stories. Thanks for watching, and see you in the next one.